Hello everyone, so this is a video where we are going to discuss about the use of complex exponential for the representation of sinusoids. Normally sinusoids are represented by sine and cosine functions, but instead of that, if we use complex exponential, then there will be many advantages. So those things we are going to discuss here. So complex exponential for sinusoids. Okay, so let us take one sine function, a sinusoid is represented by sine function, suppose with the amplitude 4 and angular frequency omega. Okay, so we can also represent the sinusoids using cosine function also, cos omega t, and it is only difference is that this function cosine omega t, that is pi by 2 phase ahead of sine omega t. So now we are not using cos omega t, we are only using this sine function for representation of the sinusoids. Okay, and we are considering here zero phase offset. We are not considering any phase offset. Okay, so now this omega t, it gives the phase information. This is the phase of the signal, and it gives the amplitude. Okay, so suppose at some instant of time t, dash, suppose this phase become 30 degree, phase becomes 30 degree. Okay, so if we put back this phase here in this expression, we will get 4 sine 30 degree, 4 sine 30 degree half 2. Now this 2, it gives the strength of that signal or the y displacement at that instant of time t dash. Okay, but now this 2, it is not giving any information regarding the phase as well as the amplitude. Okay, but instead of this, if we use complex exponential to represent the same sinusoids, we can use the complex exponential in this form: 4, that is the amplitude, I omega t. Omega is the angular frequency. Okay, and this is also periodic function. We can prove this thing by putting the value instead of t plus the time period. If you put, and you can see that we can obtain, okay, 4e omega t plus t, 4 e to the power I omega t into e to the power I omega t, and t is twice pi by omega, that is the time period. Okay, 4 e to the power I omega t, e to the power I twice pi, then e to the power I twice pi is equal cos twice pi. Using Euler expression we can find I sine twice pi, and it will give cos twice pi is equal to 1, sine twice pi is equal to 0. So it gives 1. So it will become 4i omega t. Since it is repeating, so it is a periodic function. Okay, that is uh, different point. So now what we were discussing, that instead of writing that sine function, we are using here complex exponential to represent that sinusoids. Now if we use that Euler expression again to write this complex exponential in polar form, it will become cos omega t plus I 4 sine omega t. Okay, so here now this 4 cos omega t, this function, it is a sinusoid, and it is the real component of this complex exponential, and this 4 sine omega t, that is the real component of this complex exponential, and that is the imaginary component of this complex exponential. Okay, so if you plot this one, and we can also plot this complex exponential, and this real part of this complex exponential and imaginary part. So this will be the real part because it is a sine cosine function, and so cosine function is looking like this, and this is the real component of this 4I omega t. And if we plot the imaginary component, it is a sine function t, that is the imaginary component of this exponential. Okay, so now that is one point. Now uh, let us talk about that instant of time t is equal to t dash, where the phase angle become 30 degrees. So if we put omega t dash is equal to 30 degree here, we will have 4 cos 30 degree plus I 4 sine 30 degree. Okay, so we'll have 4 root 3 by 2 plus I 4 into half. Okay, so this is the value of complex exponential at that instant of time where phase is 30 degree. So if you compare this this term and this term here, if you see in this 2, we have lost the information regarding the phase and the amplitude of the signal. Okay, 2, it cannot say about the phase as well as the amplitude information. But here in this form, if you see, we can obtain the amplitude of this complex number. How? 4 half whole square, it will give the 4. And similarly we can obtain the phase of this complex number, and we know already that phase is 30 degree, but we can also obtain that thing using the argument of this complex number, that is tan theta. It will give 4 half 4 root 3 by 2 1 by root 3, means theta is equal to 30 degree. Okay, so from this expression we can obtain the information regarding the amplitude and phase, but here from these two we cannot have the information about the phase or about the amplitude, because if you multiply 3 into 1 by 1.5, then also you will have 2. So here we have lost completely about the information about the phase and amplitude. Okay, but here in the complex exponential form, these informations are still there. Okay, now see these two components. This is the real components and this is the imaginary components when the phase is 30 degree. So uh, this imaginary component, if you see, if we started the sinusoids using y is equal to 4 sine omega t. Okay, so some at that instant of time t is equal to t dash, it becomes y is equal to 4 sine 30 degree. So here the information about that instant of time, that is the 2, we can obtain from this component. It is the imaginary component. Here we are considering the imaginary component because at the starting we took the 4 sine omega t. Okay, so all these three informations we can obtain using the complex exponential. In addition to that, if we use complex exponential in the case of manipulation of these sinusoids, when we are talking about the superimposition of many sinusoids, then addition of these complex exponentials is much easier than the addition of many trigonometric functions. So this use of complex exponential, uh, with the use of complex exponential, this mathematics also becomes easier to handle. Okay, so all this due to all these advantages, we normally use complex exponential to represent the sinusoids. So thank you very much. And if you are still having some doubt and confusions, you can ask me in the comment section. Thank you very much.